Okay, welcome back. So we are in module 4 and lecture 5, and we will be discussing about the membrane processes for wastewater treatment. So the topics covered during this lecture will be on MBR for industrial wastewater treatment. That is, we will be discussing about how the membrane bioreactors can be used for treating the industrial wastewater. Then we'll discuss about the advantages and disadvantages of the membrane technologies. We'll also talk about the disposal of the concentrated waste stream that is generated from the membrane processes. We'll also talk about the technological advances that needs to be done so that we can overcome the difficulties that we face during the membrane processes. And lastly, we'll discuss about some of the design problems related to the membrane processes. So when we talk of the treatment of industrial wastewater by MBR, we already discussed that a conventional activated sludge plant can become a single step process, and it can produce a very high quality effluent which can be potentially reused as agricultural purposes or for any other reuse like for the industrial purposes also. Okay, so the use of MBR technology for industrial wastewater treatment has gained attention because of the robustness of the process. The robustness of the process comes from the long SRT that can be maintained in the membrane bioreactors, because we know that the membrane, it retains the biomass and it does not allow the biomass to go outside the reactor, which leads to the long sludge retention time, or we can say the sludge age increases, and because of which there can be development of certain special microorganisms which may lead to the better removal of the refractory organic matter which otherwise may not take place in the conventional treatment systems. And the robustness of the system may also lead to bear the load variations as well as the toxic shocks that can arise because of the industrial wastewater that is generated from different type of industries, where we can have generation of toxic effluents. So the treatment of the industrial wastewater by MBR. So here we can see that the MBRs are very efficient in removal of the COD, even at a BOD by COD ratio of around 0.1 to 0.2, and we can achieve nearly 80% of the COD removal by using membrane bioreactors. Whereas in the conventional technologies, at a ratio of around 0.2 to 0.3 also, we can only attain COD removal efficiency of nearly 60% only. Whereas if we talk about the conventional technologies, so they generally perform at a BOD by COD ratio greater than 0.4, and they may attain a higher treatment efficiency, but it has a limitation that the BOD by COD ratio must be greater than 0.5 or 0.4 in this case. So that's why it is a very important technology, so that can be used at a very low BOD by COD ratio, and it can lead to the removal of COD of nearly 80%. So as we can see that the conventional activated sludge process system, we have already discussed about this process, and it is having a biological tank and a settling tank. So the settling tank can be replaced by a membrane that can be put as a side stream process. So this is the first generation process that has happened, that is the membrane was put outside the tank. It was doing the work of a secondary settling tank, and the retentate or the concentrate that is generated, that can be recirculated back to the aeration tank. So the second generation technology, where the membrane can be submerged into the aeration tank and effluent can be withdrawn from the membrane, and this is known as the submerged MBR. So this is how the evolution of the membrane use in conjunction with the bioreactor has taken place, and we can see that such type of MBR can be very beneficial, and they can also lead to the removal of certain processes which may be required during the conventional treatment process. So they can actually reduce the cost of the installations. So for example, if we see the textile wastewater here, so it is passing through the screen or grid, when then it passes through the primary settling, then it goes to the oxidation, and nitrification. Then it goes to a secondary clarifier, that is secondary settling. Then clariflocculation is needed, after which the ozonation of the textile wastewater needs to be done, after which it passes through a sand filter, it passes through the granular activated carbon, and we add sodium hypochlorite here so that disinfection can be done, and later on this water can be directly put into the river, or it can be mixed with the fresh water so that it can be reused for the industrial purposes. Whereas if we replace it by the membrane technology, or if we install a membrane bioreactor in place of this, so we can have a lot of units that can be curtailed. For example, we may not require the primary settling, or we may require a here micro strainer here, after which it can go to the oxidation tank or the aeration tank, and then it can go through a side stream membrane, and this side stream membrane, the permeate basically may go for the ozonation purpose, and the retentate or the concentrate may be again taken back to the aeration tank. Whereas this after ozonation, the water may go to the equalization chamber, and after the equalization chamber, we can also add here sodium hypochlorite for the disinfection purpose at this point only, and then it can go to a tank where the dilution may be done by the fresh water, and then the water can be used back by the industry. So in this way we can see that a number of units, like for example here the secondary settling tank, the clariflocculation, so these all systems have been removed when we are using MBR in place of the conventional treatment systems. Similarly, we can see that the sand filter, the granular activated carbon, these all processes are removed during the treatment by using the membrane bioreactor. So this leads to not only the compact treatment scheme, but it also leads to the reduction in cost in some way. And that is, we do not need to have a bigger installation like secondary settling tank or clariflocculator. So these things may be removed. Similarly, we have removed the GAC as well as the sand filters. So this may reduce the cost of the overall treatment process. So similarly, the membrane bioreactors have been applied for the oil contaminated wastewater. So we can see here that if we are using a membrane bioreactor, and if we are using the membrane application, that is plain filtration by membrane, and when we are using a membrane bioreactor, so we can see that the effluent COD here may be only 129 to 131, whereas in membrane application it may be around 373 milligrams per liter in the effluent. Similarly, the oil may be reduced to around 0.036 to 0.35 milligram per liter, whereas it may be around 1 milligram per liter in case of the simple membrane application. And COD removal efficiency is nearly 97%, and oil removal efficiency is nearly 99.9% in comparison to the efficiency of the removal of COD by membrane application only, that is around 85.6% only, whereas the oil removal is only 99.2%. So we can see that the membrane bioreactor can be highly beneficial for an industry where the effluent is being produced which is contaminated by oil. Similarly, we can have another example where olive mill wastewater can be treated by using the membrane bioreactor. For example, you can see here that during the electrochemical process, the phenol input is nearly 1520, and the removal of phenol that has been achieved is greater than 90%, and COD removal achieved is nearly 35 to 15%. Similarly, in the electrocoagulation also only 52% of COD removal is reached. Similarly, for the USB reactor, nearly 70% of the COD reduction takes place. And similarly, in CAC reactors, so we are having nearly 70 to 74% of removal of the phenol, whereas 30 to 65% of the COD removal takes place. Similarly, if we apply the fungal lacase, in that case also it is very low. And similarly, if we are having pleurotus as the applied for the removal of the olive mill wastewater, so it can be only nearly 69 to 76% of phenol can be removed, whereas in case of membrane bioreactor we can achieve efficiency of greater than 92%, and similarly the COD removal simultaneously can be reached up to 37 to 81%. So this is how we can see that the COD removal efficiency not only enhances, but a particular pollutant, for example in this case the phenol, so that can be removed perfectly by using the membrane bioreactor. So now we can also have a certain hybrid systems which have just now come into existence, where we can combine different type of processes, so, and as well as the membrane, so that we can reach a highly efficient and robust process for the treatment of industrial wastewater. For example, we can see here, this is an anaerobic hybrid membrane bioreactor. So it is also called ANHMBR. So this type of reactor can be used where we can have the suspended growth systems, we can have the attached growth systems, and we can have the membrane also attached here, so that we can get a high quality effluent. So this type of system has been applied for the treatment of synthetic leachate, and the leachate is a liquid which is generated from the landfill site, which is having a very low pH values, a very high COD values, and it is having a lot of concentration of heavy metals into it. And such type of leachate can be treated easily by using a hybrid membrane bioreactor. Hybrid basically means that is we are having the suspended growth systems also, we are having attached growth systems also, as well as we are having the membrane process involved here. The treated wastewater passes through the membrane, so it produces a very high quality effluent. So we can see here that this is the upflow system, and in the upflow system we are having the sludge blanket. The sludge blanket, we are having the suspended growth of the microbes that are taking place, and because this is a anaerobic hybrid membrane bioreactor, so the gas production is also taking place from here. So this is the gas production that may take place, the biogas is getting removed. And similarly, we are having a system here which is having the attached growth systems, that is the microbes are growing on a certain media. So in this case, it is a polyurethane foam on which the microbes grow, right, and they treat the wastewater. And this also leads to the less load on the membrane, in the sense that it does not allow the MLBSS to go directly to the membrane, and reduces the load of the MLBSS on the membrane. So such type of systems are also being used, and it has been found that the raw leachate can be treated by such a reactor, and it is having an efficiency more than 80% when the raw leachate is being put onto such type of systems. So these systems are quite robust systems that are now being developed, and they are in research. So now there can be certain advantages and disadvantages of the membrane technologies. For example, we are talking here of microfiltration and ultrafiltration. So the advantages are that it can reduce the amount of treatment chemicals that may be involved during the treatment of the water or the wastewater. So a lot of chemicals may be required during the treatment. It reduces their amount. For example, we have talked about the treatment of the textile wastewater in the previous slide. So there we have reduced the clariflocculator because of the application of the membrane. So the clariflocculator also requires some types of chemicals that needs to be added, which can be replaced by the membrane treatment. So similarly, the smaller space requirements are there. So it requires a small footprint, and because of the membrane, so we have already seen that the secondary settling tank may not be required, right? Similarly, other filtration units may also not be required. So this reduces the space requirement of the bioreactors. Similarly, it can also reduce the labor requirement, as such type of systems can also be easily automated, and they will reduce the staff or the labor that are involved in the management of such type of plants. Nowadays, a new membrane designs are being carried out which may allow lower pressures also. So this may reduce the cost of the treatment. Similarly, it can remove number of protozoa cysts, oocysts, as well as the Hellman's ova. They can be removed by such type of systems, and similarly they can also remove the bacteria and the viruses during the microfiltration and ultrafiltration. But it can also have certain disadvantages also. For example, it uses more electricity, that is, it is a high energy intensive systems. So that's why this may be, the cost may be increased because of the input of the energy that is required for the operation of this plant. Similarly, it may also need the pre-treatment so that it can prevent the membrane fouling, as we have discussed earlier also. So membrane fouling increases the cost. So the pre-treatment also basically may be required. So pre-treatment may also increase the cost, but it may reduce the cost in the sense that the membrane fouling will not occur very frequently, which will reduce the load on the cleaning, as well as it can also reduce the load on the membrane. Similarly, it requires the residual handling and disposal of the concentrate that is generated from such type of process. So this may be one of the disadvantage, and it may also require the replacement of membranes, which are quite costly. So this may add to the cost of the operation and maintenance. The scale formation on the membrane is also a very serious problem which can reduce the flux, and the flux basically declines gradually over time as the scale formation or other foulants are present in the water or the wastewater. So the flux rate gradually declines and we have to go for the cleaning, right? It can be physical cleaning, that is simply by water, or it can be chemical cleaning once the flux declines to such a level that we have to replace the membrane. So this may be one of the disadvantages of such technique. So for the RO process also, the advantages may be, for example, it can remove the dissolved constituents, it can disinfect the treated water as we have also seen in the ultrafiltration, it can remove certain targeted compounds like here the NDMA is there, this and other related organic compounds, so they also can be removed by the reverse osmosis process. Similarly, we can also remove the natural organic matter which is present in our wastewater or in case of water also. So these natural organic matter can be easily removed by RO processes. So disadvantages can be for such type of RO system may work very well on the groundwater which is having very low solids, or it can be basically also work on the surface water which are pre-treated or they are having very low solids. So they also can be treated by using RO process. Similarly, the wastewater effluent can also be treated, but the wastewater should be pre-treated before it is taken to the RO process. Similarly, there is a lack of the reliable low-cost method of monitoring performance. For example, when we talk about targeting of certain compounds which are present in the water or wastewater, so we have to perform a certain high-cost analysis so that we can monitor such type of compounds whether they are removed by the system or they are not removed by the system. So there is a lack of the low-cost method of monitoring of the performance in such a cases. Similarly, it may also require residual handling and disposal of the concentrate. So this may again add to the cost, and such type of systems, they are quite costly, not only in the sense of the capital cost but also during the operation as it requires very high pressure. So now one of the topic that we are discussing is the disposal of the concentrated waste stream. So this can be one of the major problem that arises because of the membrane treatment systems. For example, if we are having a small facilities where water filtration is taking place, so it can be blended with the wastewater flows and where it can be treated further. And the nanofiltration and RO basically concentrates, they may contain high amount of hardness, it may contain high amount of heavy metals, it may contain high molecular weight organics which are present, it may contain microorganisms, and it may also contain hydrogen sulfide gases, etc. And because whatever we have removed from the water or the wastewater, so that is concentrated, and these type of things now they appear in the concentrated form. So it is very important that we dispose it of properly so that no contamination or the environment is not impacted by such disposals. So for example, if we are having a simple brine solution which is coming out from the treatment by the membrane process, so this can be put into the ocean discharge, but it should be only a concentrated brine solution, but here it should not contain other contaminants, so that can be put into the ocean directly because the ocean also contains high amount of salt. Similarly, it can be also disposed of to the surface water. It should not contain any other contaminant into it. The land application of such concentrate can also be done, but it should be having a low concentration of the brine solution, otherwise it may impact the fertility of the soil. Similarly, for small discharges where TDS are not significant, it can be directly put into the wastewater collection systems. It can also be put into the sewer lines, but it should not increase the TDS, the total dissolved solids, to a significant level. Similarly, we can also think of the deep well injection where the concentrate may be put to the deeper aquifers, right, which are not connected by the surface aquifers. So there also we can put, but again we have to see that the water may not also contain certain type of contaminants into it. And similarly, we can also go for evaporation ponds where large surface area may be required. We can also go for the controlled thermal evaporation which is again energy intensive process, and because it may be the only option, that is if temperatures are not very high in the cold climate, so we can go for the controlled thermal evaporation of such type of concentrates. So then there are number of technological advances that are taking place so that this type of technology, that is the treatment of the water or wastewater by using membranes, so it may become feasible. For example, nowadays people are working on smart membranes where they are researching on self-healing or anti-fouling properties so that it can enhance the longevity as well as it can reduce the maintenance costs of the membrane bioreactors. So again, the membranes that are being produced, for example, if they are self-healing or they are having anti-fouling properties, so they may be costly. So the cost is a very important factor, and now people are working that they can develop the smart membranes at a lower cost. Similarly, we can also go for nano material integration where the membrane can be incorporated with the nanomaterials, which again can improve their selectivity, it can enhance the permeability, it can also improve the overall performance of such type of membranes. Similarly, the forward osmosis and pressure retarded osmosis are also being tried so that the energy efficient water treatment can take place and we can harness the osmotic gradients and we can go for a feasible water treatment process. And similarly, data analytics and artificial intelligence are also being introduced or included so that we can go for the real-time monitoring, we can go for the control of such systems, we can go for the optimization of the membrane processes, we can improve the efficiency, and ultimately we can reduce the operational cost of membrane processes. So now let us take one design example where we are having a brackish water which is having a TDS concentration of around 3000 grams per cubic meter. This needs to be desalinized by a thin film composite membrane, that is TFC membrane. It is having a flux rate coefficient of 1.5 into 10 to the power minus 6 per second. It is having the mass transfer coefficient of the solute as around 1.8 into 10 to the power minus 6 meters per second, and the product water that we should have, it should not have more than 200 grams per cubic meter of TDS, and the flow rate is around 0.01 grams cubic meter per second, and the net operating pressure that we need to apply is around 2500. If we assume that the recovery rate is 90%, then we have to estimate that what is the rejection rate. Recovery rate means that is how much water we are recovering. So this is around 90% water we are recovering from the membrane process. The rejection rate means that is how much salt is being rejected by such a process, and what is the concentration of the salt in the concentrate stream. So we can use the equations that we have already discussed in our previous lectures. So here the flux of the water through the membrane, so it can be given by the mass transfer coefficient of the water through the membrane and the pressure gradient. Basically, that is, here we are saying the net operating pressure, that is the average pressure gradient which is applied and minus the average osmotic pressure that is there. So this gives us the value of the net operating pressure. So this is already given to us, that is 2500 kgs per square meters, and we are having the Kw values can be put here. So we can get the value of the flux of the water through the membrane, which is again in kgs per square meter per second. And this is equal to the Qp divided by A, that is the permeate flow of the permeate passing through the membrane divided by the area. So here we are having the permeate that is going is 0.01 cubic meter per second, and then we can calculate the area from here, and this area comes out to be 2667 square meters. So now we can also estimate the TDS concentration by using the equation of the flux of the solute. So flux of the solute which is passing through the membrane is equal to the mass transfer coefficient of the solute, that is basically the change in the concentration that is passing through the membrane. So this is equal to the total mass of the TDS in the permeate divided by the area. So here we can see that the Qp into Cp, where basically this Qp into Cp is the total mass of the TDS. So this is equal to Ki into delta Ci. So this delta Ci can be written as the concentration of the TDS in the feed plus concentration in the concentrate divided by 2 and minus the concentration that is going out in the permeate, so into the area. So this gives us the total mass that is basically going into the concentrate. And here you have to assume that the concentration in the concentrate is equal to the concentration in the feed. Then only we can solve this equation for our Cp, that is the concentration in the permeate, and this gives us the concentration in the permeate. Similarly, we have to also assume that the flow of the permeate is equal to the recovery into the flow of the feed. Okay. So this can be solved for the concentration of the permeate, and we get a value of around 0.152 kgs per cubic meter from here. So this concentration of permeate, it should be less than 200 grams per cubic meter. So it is less than 200 grams per cubic meter. So we can also go for blending with the water further, so that we can further reduce the area. Okay, but it is okay that we are getting the concentration of TDS less than 200 grams per cubic meter. So now we can estimate the rejection rate by using this equation, that is rejection rate is equal to the concentration in the feed minus concentration in the permeate divided by the concentration in feed. And we have already seen that the concentration in feed is 3 kgs per cubic meter, whereas the concentration in the permeate is 0.152 kgs per cubic meter. So we can get a rejection rate of around 95%, that is around 95% of the TDS is getting rejected or it is going in the concentrate. So now we can also calculate the concentration of the TDS in the concentrate. So that can be calculated by applying the mass balance, where QF into CF, that is the total concentration in the feed, is equal to the total concentration in the permeate and plus the total concentration in the concentrate. So by applying this mass balance equation, which we have already discussed in the previous slides, so we can get the concentration of the TDS in the concentrate, and we can get easily here, that is the concentrate, the Q feed is around 0.1 liters, whereas the CF is around 3 kgs per cubic meter, whereas the QP is around 0.9 liters, that is the permeate flow of the permeate is around 0.9 liters, and we are getting here the QC around 0.1 liters, and we can get a concentration of the TDS in the concentrate is around 31.4 kgs per cubic meter. So it is really very high. So then another question is on the silt density index, which we have already discussed in the previous slides, and the test run time is around 30 minutes. The time to collect the initial 500 ml is 2 minutes. Time to collect the final 500 ml solution is 10 minutes. So we can just apply this equation for the SDI, that is 100 into 1 minus Ti by Tf divided by total time. So we can get a value of around 2.67. So 2.67, if we can see in the table that we have given earlier, so we can see that the SDI value should be less than 3. So it means that we do not require any pre-treatment, or the water can be treated by using the RO process. But because the SDI values, so they are very close to 3, so it may be prudent that we contain some pre-treatment, so that we can prolong the filtration cycle, or we can enhance the age of the membrane. Then another question that comes here is the estimation of quantity and quality of the waste stream. The total quantity of water that must be processed by using a RO process. So it produces around 4,000 cubic meter per day of water for industrial cooling operations, and we assume here that the recovery and rejection rates are equal to 90%, and the concentration of the feed stream is around 400 grams per cubic meter. So we have to calculate the quantity and quality of the waste stream. So we know that the recovery rate is QF by QP into 100, and we also know that the flow of the feed is equal to flow of the permeate plus flow of the concentrate. So by applying these two equations, equation 1 and 2, we can combine and we can calculate the flow of the concentrate, that is QP is 1 minus R divided by R, where R is the recovery rate. So we can put here, that is R here is 0.9 in fractions, right? And we know that the QP value is 4,000 cubic meter per day. So we can get the concentrate flow to be around 444 cubic meter per day from here. Now we can apply the flow balance equation here, and we know that QP is 4,000 and 444 we have just now calculated. So we can say the flow of the feed is 4,444 cubic meter per day. And similarly, we can also calculate the concentration in the permeate. So this is equal to the concentration in feed into 1 minus R, where R is the recovery rate, right? So it is basically 1.9 only, that is we have assumed 90% for the recovery as well as for the rejection. So we can get the concentration of the permeate nearly 40 grams per cubic meter. We can also find out now the concentration in the waste stream. So the concentration in the waste stream can again be found out by applying the mass balance equation. So this mass balance equation gives us, we know the values of QF, CF, as well as we know the values of QP, CP. So everything is known to us. So we can calculate the concentration in the concentrate. It is around 3,643 grams per cubic meter. So these are the references that I have used during the preparation of these lectures. So with this, we come to the end of the membrane technologies for the wastewater treatment. Thank you.